Hi guys, today we're going to learn about minerals. And that's because, well, Earth is made out of rocks and rocks are made out of minerals. So in order to understand how Earth works and what our planet is even like, we need to know what it is made from. And minerals come in all kinds of different shapes, sizes, and colors. Some are absolutely beautiful, some are kind of not that beautiful. But today we're going to learn how minerals form and, in fact, just what is a mineral. So, in order for something to be a mineral, it has to have 5 specific characteristics. First of all, it needs to be naturally occurring. It can't be something that we cook up in a lab somewhere. Nature has to make it. It also is usually inorganic. And what we mean by inorganic is it doesn't have these carbon-hydrogen bonds in there like organic molecules do. Now I have to say that it's usually inorganic because there are a few exceptions to this, but they are relatively rare minerals that you won't really see very often. And so just remember, carbon-hydrogen bonds. It can have carbon in it, it can have hydrogen in it, but they can't be bonded in a specific way. So anyway, most minerals are inorganic. Minerals also have to be solid. And they have to be a crystalline solid. What a crystalline solid means is that the atoms in the mineral are arranged in an orderly pattern. So let's look here at this display and imagine that these little ping pong balls are atoms. Notice here they're in a very chaotic organization. Over here there's a definite repeating pattern. That's crystalline, that repeating organized pattern of atoms. This is not crystalline. You can have solids that are not crystalline. Things like glass has the atoms like this in a chaotic arrangement, so it could not be a mineral. Now also, minerals must have a well-defined chemical composition. That means we can write a chemical formula for them. And so for example, a mineral called halite, which is rock salt, the same salt you put on your food. Its formula is NaCl, it's sodium chloride, and it's always sodium chloride because if there's another element in there, it's a different mineral. So these are the 5 characteristics a mineral must have in order to, well, be a mineral. So if I ever ask a question like, is something a mineral, you need to ask yourself, well, is it naturally occurring? Is it inorganic? Is it solid? Is it crystalline? Does it have a well-defined chemical composition? And if it fits all of those, it's a mineral. Now, because minerals are basically chemicals, right? They're atoms coming together to form different substances. In order to really understand minerals, we have to have a basic comprehension of chemistry. And I understand that some of you will have recently taken chemistry, so that's cool. And some of you might never have had chemistry or had chemistry like 20 years ago. And that's why I say we're going to have a chemistry review or introduction, depending whether you had it before or didn't have it. But we just really need to have a basic understanding of these atoms that are making up our different minerals. So an atom is the smallest particle that exists as an element. The smallest piece of an element you can have, like the smallest piece of gold that you could have, is one single atom of gold. If you break it down any smaller than that, it is no longer, that element is no longer gold. So it's the smallest particle that exists as an element. Now, making up an atom are 3 subatomic particles. Subatomic meaning smaller than an atom. We have protons, which have a positive electrical charge. We have neutrons, which have no electrical charge, and electrons, which have a negative electrical charge. And in an atom, you're going to have a nucleus. The nucleus is the center part of the atom. That's where all the protons and neutrons are located. And then orbiting that nucleus are the electrons. And they orbit around the nucleus in what are called electron shells or electron levels. Different chemistry books use some slightly different terms. I tend to use electron shells. Each electron shell can hold a specific number of electrons. So this first one can hold up to 2 electrons, which means it could have none, it could have 1, it could have 2, but it can't have any more than 2. The next shell can hold up to 8 electrons. And then the next shell after that is, again, up to 8 electrons. And why this is important is because how many electrons are in that outermost electron shell is going to affect how likely this atom is going to be to bond to other elements. And we'll take a look at that in a little bit. But basically, the outermost electron shell is going to affect the minerals that can form, because it's going to affect how the different atoms want to bond with each other. Now, an element, I've used this word already, an element is a substance that cannot be broken into a simpler substance by ordinary chemical or physical means. This means if you do have a piece of gold and you hit the heck out of it with your hammer, you're not going to make anything other than smaller pieces of gold. Ordinary means are things you could do in your garage, right? You can break elements down into simpler substances, but you need those like atom smashers and stuff. This is not ordinary stuff that you would do. So, substance that cannot be broken into anything simpler by ordinary means, normal things we would do. Now, every element has an atomic number. The atomic number is the number of protons, and that defines what the element is. Like, if it has 1 proton, it is always hydrogen, never anything else. If it has 2 protons, it's always helium, and 3 is always lithium, and so on. So if we look at this periodic table of the elements right here, you'll notice right up there in the upper left-hand corner that says 1, and then there's hydrogen, and its chemical symbol is H. There's 2, helium, chemical symbol He, and so on. So those atomic numbers are how many protons it has, and that defines what element we have. Now, every one of these elements also has a mass number, and this is the number of protons plus neutrons. And you'll see this other little number in the periodic table down there. That's the mass number of it. And we count the protons and the neutrons and ignore the electrons, because the electrons have a negligible mass. It is so minute that it just doesn't count. So protons plus neutrons equals the mass number. Now, you do have some elements that have isotopes. And isotopes are varieties of an element with different mass numbers, which basically means they're elements that have different numbers of neutrons. And a good example of one of these would be oxygen. You have oxygen, let's go back here. Oxygen's right there. Oxygen has 8 protons, and there are 3 varieties or 3 isotopes of oxygen. There's oxygen 16, 17, and 18. And what those numbers refer to are their masses. Oxygen 16 has the 8 protons and then 8 neutrons to make 16. Oxygen 17 has 8 protons, 9 neutrons, and then of course 18 is 8 protons and 10 neutrons. That's a stable isotope. Stable means nothing's going to happen to it over geologic time. We also have unstable isotopes, and those are things like uranium, some varieties of potassium and carbon. And unstable isotopes are what we call radioactive. They actually will decay, they'll break apart eventually, and that's something we will talk about a little bit later on in the semester. All right, a little bit more in our chemistry review. You can have atoms or molecules that are ions, and these ions have an electrical charge. So it's either an atom with a positive or a negative charge to it. And this happens because, remember those outermost energy shells I was talking about? Well, atoms like those to be filled. They like the outermost energy level to be completely filled with electrons. And so, for example, here we have our typical chlorine atom with 1, 2, 3, 4, 5, 6, 7 electrons in the outermost shell, and it wants 8. And over here we have a sodium atom, which has just one lonely electron in the outermost shell, and it really wants its outermost shell to be filled. So what happens is the sodium atom happily gives away that electron, so now its outermost shell is full, and the chlorine atom happily takes that electron, so its outermost shell is full. The only thing now is, since the chlorine atom has that extra electron, it gets a negative charge. And since the sodium atom got rid of that electron, it now has a positive charge. So that's how these ions get their charges. They either steal an electron or give away an electron. Now, there are then, of course, going to be two types of ions. An ion with a positive charge is a cation. One with a negative charge is an anion. Now, this becomes important because, like I said earlier, minerals are simply atoms bonding together. And the characteristics of a mineral are going to then be affected by how those atoms bonded together. And one of the types of bonding that we are concerned with in mineralogy, at least at this level of it, is an ionic bond. An ionic bond is where these ions of opposite charges are attracted to each other, right? Opposites attract. And so again, that's like our sodium and our chlorine, right? We ended up with our positively charged sodium because it gave up that electron, our negatively charged chlorine. So now you have these opposite charges are attracted to each other and stick together with each other. This is not the strongest bond around. Now, a different type of bond that is much stronger is called a covalent bond. Covalent bonds occur where atoms share electrons. So what we're seeing here, we've got these unhappy fluorine atoms because they only have 7 electrons in their outermost shell and they really want it to be full. And so what ends up happening is they start sharing some electrons. So those electrons are going to orbit both atoms, and that's going to make the atoms feel like their energy shell is filled, and so now they are happy. They're sharing these electrons, and this is a stronger chemical bond. Now, another bond that's important in mineralogy is a metallic bond. And in this case, you have electrons that move freely among a number of different atoms, and they're not really specifically associated with a single atom. So we have, our atoms, and then we have some of these electrons that just sort of happily wander amongst various atoms, which is also why metals are very good at conducting electricity. Now, at this level, at this introductory geology level, I just want you to know about these 3 basic types of bonds. If you go on studying geology, you will eventually learn about things like van der Waals bonds and hydrogen bonds and stuff like that. But don't worry about those at this point in time. All right, one of the major characteristics of a mineral is the fact that it is crystalline, right? It has that orderly atomic arrangement. And crystallization is where these atoms and molecules come together and they bond in this repeating orderly pattern. And so this is what table salt, halite, looks like, right? We have chlorine, sodium, and it just repeats over and over and over again. Now, some substances have what are known as polymorphs. And a polymorph is a mineral that has exactly the same chemical composition, but it has a different crystal structure. And probably the classic example of a polymorph is where we're dealing with native carbon. Native meaning pure. So we have pure carbon. Pure carbon could be a diamond, like this mineral, or it could be this mineral, graphite. And diamond is the hardest mineral, and graphite is one of the softest. And why is that? Well, if we look at the way the diamond is bonded together, all the little carbon atoms are bonded with these strong covalent bonds. If we look at the graphite mineral, the carbon bonds are bonded not in 3 dimensions, they're bonded strongly in 2 dimensions, and then there's these weak bonds. So when you're writing with a pencil, I know we call them pencil leads, but it's actually graphite that you're writing with. And what's happening as you write and you drag that pencil across the piece of paper, you're basically rubbing off these sheets of that mineral and leaving them behind on the paper. And the reason you get these different types of bonds is the conditions that the mineral forms under. If we're under higher pressure, you'll tend to get these strong covalent bonds in 3 dimensions. Not so high pressure, you get these types of bonds. So exactly the same chemical composition, but those atoms are bonded together differently, so you get very, very different characteristics in the mineral. All right, so minerals form in kind of 5 basic ways. So there's 5 ways we can get naturally occurring minerals on Earth. And one way is a melt can solidify. Melt meaning something liquid cools down and becomes solid. Another way of saying this is freezing. So right here we have a lava flow, right? And in that lava flow we have all kinds of different elements. And as that lava flow cools down, those different atoms are going to line up and bond with each other and form minerals. And so these older lava flows that are already solid, you can just think of it as rock has frozen, right? It's dropped beneath its solidification temperature, went from a liquid to a solid. And that's one way we get minerals, solidification from a melt. You can also have precipitation from a solution. Well, in this case, this is where you have atoms that are soluble. They can dissolve in water. Probably the best example around is salt, right? You take some salt, pour it into water, stir it up, the solid little salt crystals disappear. Well, it's not like they magically went away, they're just dissolved in the water. And there are other minerals that can dissolve in water like that. So then what happens is we have this salty water, and as that water evaporates, then whatever's dissolved in it is going to be left behind. And that's what we're seeing right here. This is Badwater Basin in Death Valley National Park. This is very, very salty water that is evaporating, and as it's evaporating, it's leaving this white stuff behind. That happens to be salt. That salt was dissolved in that water, and as it evaporates, that solid crystalline salt is left behind. Now, here's a weird one. It's called solid state diffusion. So diffusion is where atoms can kind of move around through a substance. And we're familiar with that happening in air and stuff, but it can also happen in solids. But it does have to happen when things get kind of hot, because when rocks get heated, the atoms in them, heat basically is the atoms vibrating. And as the rocks get hotter, the atoms vibrate more, and they can still be solid, but they can be vibrating enough that some atoms can kind of move around in there. And as they move around, they'll end up bonding with other atoms and creating new minerals. Okay, sounds weird. This happens when a certain type of mineral or a certain type of rock called a metamorphic rock is formed. We'll talk more about that when we go to metamorphic rocks. Now, biomineralization is fairly straightforward. Anytime we see this prefix bio, we should be thinking about life. Well, different kinds of life forms will take in minerals, basically elements from their food or the surrounding environment, and they will then use that to build their shells or to build their bodies, like this coral. This coral is made out of calcium carbonate, a mineral called calcite. And basically, the coral animal takes in calcium and the carbonate ion from seawater and from food, and it then uses it to build its shells. We do the same thing. Our teeth have a mineral called apatite on it. And like clams, when they're forming their shells, well, they're precipitating a mineral to create their shell. So that is where life helps the mineral form. And then the last way this can happen is through fumarolic mineralization, which is not the most common thing around. Here's how it works. We are at a fumarole. Well, a fumarole is a place where a volcano is breathing. Even when volcanoes aren't erupting, there's a magma chamber underneath there, and they give off gases from this magma chamber. A fumarole is where those volcanic gases are coming out of the ground. And many volcanic gases have a lot of sulfur in them. And that's this yellow we're seeing there. So what happens in fumarolic mineralization is a gas is coming out of the ground and it's directly creating a solid. You know how usually you have to go from solid to liquid to gas or gas to liquid to solid? This is skipping that intermediate step. And so directly from this volcanic gas coming out of the ground here, sulfur mineral is being precipitated.